Hello everyone, in this video we are trying to follow this book Cloud-Based Remote Sensing with Google Earth Engine chapter A2.5 Water Balance and Drought. In this chapter we make ourselves aware with water balance calculations using remote sensing derived products related to precipitation and evapotranspiration. And we also looked through the time series analysis of remote sensing vegetation and drought indices. And we briefly viewed the overlaying of indices with the land cover map to estimate potential drought impacts throughout the region. Our objective, like in the previous video, is to go through the chapter quickly and briefly. So why is this important? Water is an important resource. Optimization of water allocation is important for effective utilization of the water resource. And how do we study this? In the hydrological system, we try to understand the input and output in the system. So the input and the output of the water in the system. Here we have the equation by general concept. Input has to be equal to the output. So we see P is equal to Q plus ET plus delta S. P represents the input to the system, into the hydrological system. It refers to the rainfall and snow or the water that enters the system. Then we have the extraction from the system. They include runoff, evapotranspiration, again, relates to the output from that system. And we also have the delta S, which relates to the change in the water storage. So it can be changes in soil moisture, groundwater storage, and surface water storage. And the particular example shared in this chapter is for the Lower Mekong River Basin. It covers a few countries, Laos, Thailand, Cambodia, Myanmar, and Vietnam. So it covers multiple countries, but water is the shared resource. So the combined approach of management strategies are required. In remote sensing, we use different data related to precipitation and evapotranspiration. The first is the tropical rainfall measuring mission, TRMM, which was the joint mission of JAXA and NASA, intended for studying the tropical rainfall. Then we have the Global Precipitation Measurement Mission, which is the successor of TRMM. And we also have the GERPS data for the rainfall. And these all data can be explored in Earth Engine. So for evapotranspiration, empirical models are prepared relating with the spectral reflectance. So MODIS is the mostly used for the preparation of evapotranspiration data. So there are different algorithms, and we frequently use MOR16 algorithm. MOR16 algorithm uses this equation called Penman-Montet equation, and it uses the meteorological and vegetation data from MODIS as inputs. Being aware of these algorithms is not the main objective here, but this all seems very interesting on how evapotranspiration is computed. And to continue with the water balance, so we can rearrange the equation, and when we rearrange this equation, we get this portion of Q and delta S in one side and P minus E in the other side. And what our objective in this water balance equation is to calculate this P minus E, because we have the monthly precipitation and we also have the evapotranspiration, both from the remote sensing data. And also this vegetation indices are used to observe the drought. And this moisture stress index, MSI, which is calculated from the shortwave infrared and near infrared bands, has been found to be highly related to soil moisture. And this is simply the ratio of shortwave infrared to the near infrared bands. So the objective is to cover the codes very briefly and to get some idea. So here we have the very first section of the code. We begin by importing the area of interest. We import this as the feature collection. We can easily upload the save files in our engine, and we center the map with zoom level 5, just how big the map appears in this map layer. Then we add this as the layer by map.addLayer. We set the two different years, the starting year and the end year, and we create the two date objects from that 2 years. The function here is e.date from YMD, and this gives us the date for that year. So in this case, here we have 1 and 2 ones, 1, 1, and the start year. So this will simply give us the first date, or the first day of the year 2010. Similarly, for the end date, we are doing this for the first day of 2021. So we have the starting year as 2010 and ending year as 2020. And then we make the sequence. ee.list.sequence creates the sequence of the number. In this case, the sequence is for the number of years, and similarly, and this can be also done for the months or any other sequence if necessary. We import the chirps data set, and we filter it by dot filter date. Here we have the start date and end date. Then we apply this loop called the nested loop. Basically, it goes through the years and it also goes through the months. And this returns the monthly sum of the images. So basically, this nested loop means we create the function inside which we create another function. So we can see here, we had created the sequence of the years, and this sequence of years is mapped with the function here. And inside that function, we are creating another function for the months, and the chirps data is filtered by the years and filtered by the months as well. And we do dot sum for summing up the total precipitation for that month. Then we return the summed image by return here, with the year as the property, month as the new property, and then time start property with assigning the date. So basically, this dot set assigns or adds the new properties to the final returned image. So this is the way to get the monthly images. And here this dot sum is used, but we can do means, medians, or anything we want. And we can edit it and use for any other raster datasets. And in the end, we also see this dot flatten. So this has the very important function. This kind of converts the feature collection of features into a single feature collection. So this is to just simplify our feature collections. And this whole collection that is being returned is being made into the image collection. So this image collection dot images makes this whole images into a bundle, into a image collection. Then we see the visualizing parameters for this precipitation. We have the minimum and maximum values, and then the list of colors. We finally display the mean image. So we do the mean of all the images, and then we add this as the layer. And we have some title and axis levels for the chart, simply to be used later here. And we chart by this function here, ui.chart.image.series by regions. So our image collection is the monthly precip here. This is the variable name. And our region is this Mekong Basin. And the reducer is mean. So we are showing the mean values of that region. The band is the precipitation, and the X property that will appear in the X-axis is the time properties. Then we have the options which will appear as levels in the chart. The type of chart is column chart. Then we can print the chart and see the chart in the console. I have already printed. I've already run this, and we can already see this in the console. And in quick inspection, we see that the months September and August, generally September and August are the months getting highest amounts of rainfall. So this is the first section of in the second section, we did the same thing, but this time for the evapotranspiration, we use the Morse 16 data and repeat the same process. And this is the same thing that was just done for the precipitation data. And in the third section here, we repeat the same process, but for returning image, we do this subtraction here. So we are doing the same equation that what we had seen the last here in the rearranging of equation that we had seen P minus E. We are doing the same thing here by subtracting evapotranspiration with the precipitation. And we are renaming this as the double B. And everything is same. We also draw the chart for the monthly water balance. In the fourth section, we calculate the moisture stress index by dividing the SWIR band with an IR band and renaming it as MSI. And here we are doing the same thing. For precipitation, we are doing the sum. For evapotranspiration, we are doing sum. Here the multiply, we are multiplying with some constant just for the rescaling. The original data is stored in some other structures to minimize the storage. So we have to multiply with this constant here. And for EVI, we are doing the mean, same thing here with the scaling factor. And then we are also calculating the MSI. For MSI, we're doing this mean. This is the stress index. And then we are subtracting evapotranspiration with the precipitation. But here we're using this image.cat. So this will give us the image with 5 different bands, and we are assigning different properties to that returning image. The chart is also being created here with the function ui.chart.image.series. So we wanted to show 3 different bands, but it is showing this error of memory limit exceeded. So I haven't changed anything. I just ran this few times, but it is not really giving the chart. So there might be some problem with the scaling, with the area, and with some memories. So not sure for now. Then we have the code 5, or the 5th section. So in this, we want to overlay various indices with land cover map. And for this, the land cover of the area has been imported. So we can see the legends and different years as the layer. So this is how the legend appears in the left-hand side, and we have the layers for different years. Doing this is a different topic, but we can just copy this and use for our own use. Then we have this section where we see the amount of precipitation and evapotranspiration for different land cover classes. So we can see the precipitation is higher or highest in cropland. Similarly, evapotranspiration is also highest in cropland and in the forest, deciduous forest. And then we have the water balance for different land covers in different years. So close inspections are required for understanding this graph, but it shows the different water balance for different land covers in different months. This is very nice to see for different land covers and also for the months. And in this last section, the charts were supposed to be drawn for different land covers. For example, this cropland index, it contains the cropland only. The image is marked only for the cropland. And then we select the 2 different bands and we draw the chart. But this is again showing the error here. So there might be some problems, but overall, these all are what this chapter deals. And we certainly need to go through this again, maybe in future videos. I hope so. And this chapter contains lots of codes that can be copied for our own use. And that's the nice thing. I believe this was helpful to you at some extent. So I would say thank you for watching.